Yo, what's going on, you science nerds? So, this is going to be a quick recap of what radioactive half life is. Let's do it. All right. So, as the name implies, you see half and then life. So, when you think about the lifetime of something, that means from when something exists until it totally goes away, right? That would be the lifetime or the full life. Usually we just don't say full life, right? That sounds weird. But then we could use that to try to understand what the heck half life means. So, half life is the amount of time it takes for one half of something to go away, not all of it. So, in this case, for our topic, we're talking about how long it takes for one half of the atoms in a sample of radioactive material to give off their radiation and decay. So, something we have to look at here is when a radioactive nucleus is unstable, that's why it's radioactive, and it gives off some form of radiation. We learned about gamma rays, alpha particles, beta particles, whatever. That's kind of like having a hot plate of food or a cup of something to drink. When it cools off, it just changed to be lower in temperature, but it didn't disappear. And that's the same thing with the radioactive atoms in a sample. You see the brown dots? Those are the original radioactive atoms. And then afterwards, after one half life, half of them have randomly given off radiation and changed, but they didn't disappear. They just changed into a nucleus that's not radioactive anymore. And if you look after two half lives, it's not 100% through the original amount. It's not half of the original amount that are still the brown original atoms. It's only a quarter, so it's half of the half. So basically, what's happening is after every half life, there's only one half, right? 50% of the original amount of radioactive atoms that are still radioactive, I guess. Or you could say they're either still radioactive or they have not changed yet. After two half lives, there's half of the half, which is half of a half is a quarter. And then after three half lives, that's half of a quarter, which is 1/8. And then after four half lives, that's half of an eighth, which is 1/16. So, a couple things to remember. Why use half life? Why not use full lifetime? Well, the problem is this: when any individual radioactive atom is going to decay, is an absolutely completely random and unpredictable thing. We cannot know it. Like, you can stare at a radioactive atom for a billionth of a second in a lab using some tools, and it will give off radiation after a billionth of a second. Or the atom can take a billion years. We don't know. So we use half life to measure the change in a large sample, and we can make accurate predictions about how old it is. Another important thing that makes half-life useful is that half-life is a constant. It does not change over time, which is why we could use it to make predictions, especially as a measurement of time. Really quick, we know that radioactive carbon-14 is inside of living things, including us. And after the radioactive carbon isotope 14 gives off radiation, it becomes nitrogen-14. So basically, if we measure the ratio of carbon-14 to nitrogen-14 in a living sample, or, well, not alive anymore, but something that used to be alive, meaning biological, we can measure its age pretty accurately up to 62,000 years old. If we want to date the age of rocks and minerals, we use the naturally occurring uranium isotope 238, and over many, many millions of years, it decays into lead isotope 206. So we use uranium 238's decay to lead 206 to date rock formations. And if we want to date really old rock formations, or let's say something like dinosaur fossils, we need to use the isotope potassium 40, which decays into argon 40, because the half-life is extremely, extremely long, billions of years. So if isotope has a very long half-life, we could use it to measure things that are very old. Okay, so let's get to it. Last thing. Obviously, we use radioactive isotopes in medicine to either detect or treat diseases, but we know that radioactive atoms could cause damage to cells and cause a disease. So to prevent that, when we use radioactive isotopes in medicine, we want to make sure that they have short half-lives. So let's say a week. Like, we don't want stuff in your body that's radioactive for a very long time. And also we want to use isotopes that are easily removed by your body in, well, you could think about the ways that your body removes things, but you want isotopes that are easily excreted by your body and have pretty short half-lives of only a few days to make sure that the radioactive things don't actually damage your body, but instead we can use them as a medicine. All right, so let's practice. Honestly, I'm just going to jump right to using a data table to solve a half-life problem, and let's practice doing that right now. So if you notice the table, I like to set it up as the first row is half-lives, the second row is amount of time passed, and the third row is the amount of material. And if you notice, the fraction for the amount of material sticks to the formula 1/2 for half, and then you put 2 to the power of how many half-lives. So anything to the 0th power is 1. So 1/2 to the 0 is 1/1, which is 100%. So you're always going to start these data tables with the starting amount as 100%. And if you notice, after one half-life, that's 1/2 to the 1 half-life, 2 to the 1, or anything to the 1 is itself, right? Anything to the 0 is 1. Anything to the 1 power is itself. So 2 to the 1 is 2. So we have half after one half-life. That's why it's called a half-life. After 2 half-lives, 2 squared is 4. So we have a quarter, 1/4. After 3 half-lives, you have 2 times 2 times 2, which is 8. So we have 1/8 left. So we went from 100% to 50% to 25% a quarter. Now we have, 12.5%, 1/8, and so on. Okay? So why don't we try to redo this problem here. So it says a 30-gram sample of iodine 131 decays for 32.084 days. What amount of the original 30-gram sample remains unchanged after the 32.084 days? Okay, so let's do it. Let me see if I could get this to take up 2 screens. Nope, wrong one. Sorry. Let's go back. Second. All right, so can I get this to work? Looks like it. All right, so we need also the chemistry reference tables to do this. All right, now we're ready to roll. So let's try a couple practice problems. This first one, they gave us a starting amount of 30 grams is the amount. They said the radioactive isotope is iodine 131, and they said that the age of the sample is 32.084 days. Okay, they want us to figure out how much of the original sample is still remaining. Okay, so first let's set up the table. Half-lives, time, and amount. Okay, so half-lives, time, amount. All right, so first thing we need to do is go to the chemistry reference tables and go to reference table N. So if we go to table N, we'll find the isotope. So we're looking for iodine 131 and we're looking for its half-life. So iodine 131, there we go. The half-life is 8.021 days. So now we know that the half-life is 8.021 days. All right, so what that means is, ready, follow me here. We always start with 0 half-lives and 0 time, meaning no time passed yet. And in this example, we can use 30 grams as the starting amount because that's what they said we're starting with. All right, now we're going to go ahead to 1 half-life, and we know from the data table or reference table N that the half-life is 8.021 days. So after 1 half-life, that means that 8.021 days has passed. That's the amount of time. And the amount remaining, let me get my calculator open. The amount remaining is going to be half of 30. So 30 divided by 2, 15 grams. We're done, right? Nope. The question said use 32, not use 32, excuse me, that the sample is 32.084 days old. So that means that we have to keep going up by 1 half-life until we get the sample to become 32.084 days old. So watch how this works. 2 half-lives, that's going to be 8.021 times 2. So 8.021 times 2. 16.042 days. All right. And now, remember, every time 8.021 days passes for a sample of radioactive iodine-131, that's the half-life, meaning the amount remaining gets cut in half. So now we only have 15 grams, and we're going to divide that by 2. 7.5 grams. But the sample now is only 16.042 days old. So let's do 3 half-lives, and that's going to be 8.021 times 3. Now, do you notice I didn't do 16.042 times 3 because that's not the half-life. This is the half-life. Remember that. The half-life does not change. The half-life is 8.021 days, and that stays constant. So a common mistake I see students make is they'll use the number afterwards. No, you always stick with that number. So 8.021 times 3, or you could think about it as 8.021 plus 8.021 plus 8.021, whatever, right? So now we're up to 24.063 days, and we have 7.5 grams, but now half of that, so divided by 2, 3.75 grams. But again, we're still not done because the data given to us said that the sample should be 32.084 days. So now we're at 4 half-lives, and that's going to be 8.021 times 4, 32.084 days. That is how old they said the sample was. So now we're at half of the amount that's still there. So 3.75 divided by 2. There we go. 1.875 grams are remaining. And that is the actual answer. So out of the original 30 grams, only 1.875 grams are still radioactive. There we go. Let's try at least one more before I cut the video. How long am I up to so far? Let's see. 12 minutes? All right. Let's do one more. I bet you guys and girls can hang in for one more. Let's try it. All right. So there was one example. Let's see. This one. Let's try this. What is the age? So you notice the last question we did, we solved for the amount remaining. What about a question like this where it says, what is the age? Now think about when somebody asks you about your age. That's how much time you've been born for and still alive, right? So they want us to find the amount of time. So let's read this. What is the age of a sample of radium isotope 226 if 47.5 grams are still unchanged, so didn't give off radiation yet, and they gave us an initial amount that is 760 grams. All right, let's try this one. Ready? Let's do it. Orange. Okay, so what did they give to us? They said they want us to find the age. So age equals question mark. The sample is radium 226. The amount left, the amount remaining is 47.5 grams. And the initial amount, which in science, the symbol that we usually use for when something is at the beginning, the initial, is we put a little 0 next to it, just to let you know. So they said that was 760 grams. All right, let's do it. Data table, half-lives, time, amount. Remember, we always start with no half-lives passed, no time passed, and the starting amount, you could think about it as 100%, like the fraction 1 over 1, or we could put it as 760. I'll put both because I'll show you how that works. So 760 grams. All right, this one though, now that we know how this works, we could go a tiny bit faster. So let's see. Well, wait, we need to look up the half-life of radium-226. All right, so where's radium-226? Half-life. Radium-226 has a half-life of 1,599 years. See that? Right there. Okay, 1,599 years. That's a long time. So the half-life, 1,599 years. All right, so let's do it. So that means that after one half-life, the time that passed will be 1,599 years. And we know that the fraction left will be half of the original amount, which is, let's pull up the calc. So 760 divided by 2. That's 380 grams, which is half of the original amount. But they said that the amount that is remaining is, right? They said the amount remaining is 47.5 grams. So we need to keep going until we hit 47.5. You know what that means? That you don't have to fill in every single slot here. Watch this. We could go a little bit faster. We know that after two half-lives, that the amount remaining will drop to only a quarter, which would be, well, let's see, 380, which is the previous amount, divided by 2, will be 190. Now, to just prove to you that this works, what's a quarter? 1/4 of the original number. So let's start with the original number, 760 grams, and divide it by 4. Oh, look at that, 190. So that's why you can use, oh boy, never a boring moment. We could use the fraction or the amount. Now, is that 190 grams, which is a quarter of the original amount, is that how much they said was left? No. So what we could do is just, we don't have to fill everything in. We could just go, okay, 190 divided by 2. That's 95 grams, which is 1/8 of the original amount. Is that how much they said was left? No, they said 47.5 grams. So let's divide that by 2. Oh, look at that. 47 point, oops, wait, sorry, I'll put the fraction as well. We got down to 47.5 grams, which is 1/16 of the original amount. I could prove it to you again. 760 divided by 16 gives us that. Now, let's see. How many half-lives did that take? 1, 2, 3, 4, meaning the sample has decreased by half 4 times. So now the easiest way to wrap up a question like this is to go, okay, the half-life is 1,599 years, and this took 4 half-lives. So all we got to do is multiply 1,599 times 4. And we know that this sample is 6,396 years old about. And that's how we can use radioactive samples to date the age of things. And we spoke about it before in the lesson. That's called radiometric dating. There you go. So remember, you start with half-lives, time and amount. Half-lives is 0, time is 0. And the starting amount, it's up to you. If a question gives you an actual amount, you could put that many grams, or you could just think about it as a fraction of 1/1. Okay? All right. I think that's long enough. You probably won't want to watch more. So I hope that helps. If not, you know the drill. Ask me for more help if you need it. Okay? Good luck. Peace.